All right, great. Good morning, DevOps. Are you guys awake?
Good morning.
No response. Good morning,
Good
DevOps.
morning.
All right, cool. Welcome. We're really looking forward to give you this talk. I'm Nick. I'm working as an AI engineer at Collibra. I'm building recommendation systems and classification systems in order to help organize our customers' metadata assets.
Hi, good morning. I'm Gretel. I'm a data scientist at Collibra, and I work mainly on discovery projects to see where we can use machine learning within the product. Question, who is a Star Trek fan? Can you raise your hands? Yay!
All right.
Any Star Wars fans here?
Oh, shoot.
No, we want you to stay. Don't leave. But
Yeah, but...
be prepared to be converted, right?
All right. So today we'd like to give you a little bit of an overview of machine learning techniques to learn word embeddings, and we'll be using the Deep Space 9 scripts to do so. And we would like to bring you this story from two different perspectives. On the one hand, the data science side, and on the other hand, the engineering side. And about those two sides, next slide, please. There is a little bit of a difference, isn't there? I mean, data scientists, they just endlessly want to tinker with fancy data sets and endlessly want to try like fancy new models, transformers and such. And for some reason, they really like panda bears. I don't understand.
True, and then AI engineers, once they come in, the first thing they want us to do as data scientists is to get rid of pandas. They love refactoring code endlessly, and for some reason, you guys like mechanical keyboards, but then you need noise-canceling headsets.
Yeah, we really like them. All jokes aside, next slide, please. We'll try to keep these two perspectives into mind. We'll first jump into the data science side a little bit, and we'll interject some engineering remarks there. And in the mid of the presentation, we'll jump all the way back into the engineering side. So, next slide, please. Let's get started. Word embeddings. I mentioned them, we mentioned them. It's in the title of our presentation. But why? Right? So what is a word embedding? A word embedding is nothing but a vectorial representations of the words in your data set or the vocabulary in your corpus to be put into more fancy terms. And one very simple way for you to create them would be to use one-hot encoding. It's super easy, right? As in the example on the slide on the left. You can see, for example, man, we're just setting the first bit and keeping all other bits cleared, 0. Woman, we're setting the second bit, all other bits cleared, and so forth. This is one-hot encoding. It kind of ticks the box, right? It's a vectorial, so a series of numbers to represent your words. But let's look into a little bit of a few smarter ways to calculate these embeddings. Let's look into bag of words. Over to you, Gretel.
All right, so let's have a look at a bag of words using Deep Space 9 scripts. For those who are interested, this is actually where I downloaded all the episodes of Deep Space 9. There's many sources where you can find it, but this is one of them. And of course, here they are, all nicely loaded in a pandas data frame, obviously. So Nick described a very simple mechanism to create a bag of word representation of the... Oh, sorry. Does that work? All right. Yeah, I always have everything very zoomed in. I forgot about that. Yeah. All right, so we have our data loaded here into a pandas data frame, and we're going to apply a few different or two different mechanisms to turn this text data into a vectorized format so we can feed it into a machine learning model. The first one that we use here is just a simple count vectorizer. Sorry, wrong section. So we have the count vectorizer is the first option that we are going to have a look at. We're using scikit-learn for this particular as the implementation here. And as you can see on this simple example, it basically is going to count the number of times each of the words in our vocabulary appears in each of the documents or episodes in our particular case. A slight variation of this theme is what we call TF-IDF vectorizer. TF-IDF stands for term frequency inverse document frequency. In the normal simple count vectorizer, we weigh each word equally. In the TF-IDF vectorizer, this is not the case. We're going to weigh those words which are appearing in a particular episode more heavily if they don't appear that frequently in the rest of the corpus in the other episodes. So they receive a higher weight. The nice thing about this particular output, this vector, is also that it's already normalized. This will help us later on. So we are going to apply this TF-IDF here on our Deep Space Nine script. So we're reading in the corpus, initializing the vectorizer, and this is what the vector looks like, expanded into an array because it's a sparse matrix. And as you can see, lots of zeros, obviously. But zooming into a little slice of this matrix, we do see that there's these weights appearing where we have words in our vocabulary appearing in the episodes. So we have 166 episodes, and the total vocabulary for Deep Space Nine is 27,239 words, excluding stop words. One of these words is racticino. As we can see here, if we ask the model to give us, to tell us if racticino is in our vocabulary, the answer is true. Now, for the Star Trek fans who have seen Star Trek, obviously, if you're a Star Trek fan, sorry, nerves, they know what a racticino is, but for the rest, here's a little clip.
One racticino with a jacarine peel.
Every morning for the last year, I've seen you walk in here and start your day with a racticino.
I love racticino.
Feel like getting a racticino before we call it a night.
Tell Dr. Torvin to get a cup of racticino. He won't be needed.
I trust he wasn't vaporized while asking for one of those ractiginos he's so fond of.
Can I get you another racticino?
One ractigino extra hot, 2 measures of cava.
Your ractigino.
Guess I'll have to take my racticino with me.
Would you like another ractigino? Ractigino, extra sweet.
The chief asked me to come up with a decaffeinated ractigino for Kira.
Oh, you make me sound like some kind of addict. She has maybe 2 ractiginos a day.
All right. I hope everyone had their ractigino. So, all right. That was a little example of bag of words. We're just warming up. Back to you, Nick.
Yeah, so it has quite a few downsides, doesn't it, right? The first thing to note here is that the size, the width of this vector, it grows with the size of your vocabulary. The more words, the wider it becomes. And as Gretel already showed in her slides, it's packed with zeros, so it's very sparse. It doesn't really condense a lot of information of your words, of your text, into this representation. So, and that's actually the point we want to tackle here. We'd like to move more into the right side of this slide, into a representation where each of the dimensions, each of the bits in this vector actually convey a certain meaning. For example, man can be measured across whether he's alive, feline, human, and royalty, and some are more applicable than others, obviously. So let's look into a model that can actually automatically calculate these individual interpretations and give us a much more interesting embedding. Over to you, Gretel, for Word2Vec.
So Word2Vec is based on a linguistic theory, which is not new, has been around for quite a long time. And the theory says that we can deduct semantic meaning, or we can derive semantic meaning from co-occurrence of words. And this is sort of summarized in the saying, you shall know a word by the company it keeps. So let's have a look at our Deep Space Nine data and use we'll start by using a pre-trained word embedding. So in this case, I'm using the Word2Vec Google News 300 pre-trained embedding. And if we have a look at a particular example here, this is actually sort of the school example, right? Maybe a lot of you are familiar with this one if you have worked with embeddings. So if we ask the model to give us a vector which is positively similar to woman and king and negatively similar to man, we get the result queen. So this shows that compared to bag of words, we do get semantic meaning now in these embeddings. Let's try this out on, or let's train a word-to-vec model on our Deep Space Nine scripts. So we're reading in the data. We're defining, or we're going to initialize a word-to-vec model. We're using Gensim, in this case, the library. We decided to train it for about 50 epochs, and this took, on a normal laptop, this took less than a minute, which is really nice. No GPU required. Let's examine the model a little bit closer. So this is a little slice of the vocabulary, and if we ask the model to give us the full vector for recticino, this is it. So does this vector actually contain some semantic meaning about what a recticino is? Well, we can ask the model to give us the 5 most similar vectors to recticino, and we get things like coffee and tea and cup. So you can see that it has indeed learned some semantic meaning here. And now for a Deep Space Nine version of the king and queen example, if you ask the model to give a vector which is most similar to Kira and man, but negatively or dissimilar to woman, we do get Sisko, which I thought was pretty cool, actually, after 50 epochs. So Sisko and Kira are the 2 main characters in Deep Space Nine, and they both command the space station at different times. All right.
So this is already quite an improvement, isn't it? I mean, the size of the embedding is not growing anymore with the size of the vocabulary. Actually, it's an input of the word-to-vec algorithm. It automatically learns these different meanings by itself. Granted, this is not a human interpretable meaning like shown here for the slide, but it already captures something. So similar words have similar vectors. Now, next slide, please. Why are we doing this in the first place? Why are we capturing these embeddings? Well, we already mentioned it. They can convey some sort of meaning. So how can we compare those vectors with one another? Well, it turns out that there is quite a few ways, and I'm skipping the math here, just to be, I included it in the slide just to look fancy, obviously. But one interesting one is the cosine similarity metrics. This is basically where you're interpreting this vector into a this embedding into a vectorial space, and you're going to try to calculate between any 2 given vectors the angle in between them. And the smaller the angle, the closer they are to each other. So the more semantically related they are to each other. And in fact, that's what was happening sort of under the hood of this slide. The cosine distance is pretty interesting because, well, the math looks maybe a little bit scary, but it just boils down to a simple dot product between 2 matrices, and that's kind of basic, right? It even is super well supported by your CPU and GPU, so it goes insanely fast. And all frameworks that are a little bit serious support these kinds of operations out of the box, right? Another cool part of this cosine similarity is the fact that it's scaled, so it's nicely, well, it's normalized nicely between -1 and 1. It's a cosine, right? So that's handy. Now, next slide, please. What can we do with that? Well, in fact, if you can measure between 2 embeddings its similarity with, for example, the cosine distance, you can start to calculate what are your nearest neighbors. You just need to take any given embedding, like the one in red here on the slide, and you can start calculating the distance between that embedding and any of the other embeddings in your data set, and retain only the ones that are closest. This is called the KNN algorithm. It's kind of too simple to explain, right? And only with that neat little trick, you can already do some quite interesting things. And Gretel will show you.
All right, and let's actually even go back to our bag of words implementation. We said it's very simple, but actually, you know, simple doesn't mean bad, right? Sometimes that's maybe what you need. And we're going to have a look at the cosine similarity, comparing the episodes. Let me move to that particular section here. So finding similar documents, that's what we're going to talk about. And remember, we created the embeddings using TF-IDF. So the vector is already normalized. So if we want to do a pairwise similarity, we can simply do a dot product, which is very easy. And then we get this pairwise similarity here expanded to an array. So you can see on the diagonal, we have 1, of course, because that's the similarity of each episode to itself. So that gives us a perfect similarity, and the rest here will be between 0 and 1, because our inputs are always positive in this case. Now, how do we know if this is at all meaningful? So we have calculated, I'll move back a little bit. So we just had calculated our pairwise similarity, just creating a dot product. Of course, we're throwing this into a pandas data frame.
You see, they really like panda bears. I know.
All hail to Wes McKinney. Love it. And then from pandas, we can create this nice little heat map. And as you can see, diagonal is a perfect similarity between each episode with itself. But as you can see, this is just the first 50 episodes, because putting all 166 on one heat map was not readable. So, but what we can see is a little cluster here, right? We can see that there's a higher similarity between these 3 episodes, just using bag of words and cosine similarity. Now, how do we verify whether this is meaningful or not? Well, for, again, Star Trek fans, you might know that The Homecoming, The Circle, and The Siege are a 3-part episode. So it's actually one story that continues across these 3 episodes. So it does make sense for these, of course, to be closer together in the embedding space. And if we just have a quick look at our doc2vec, so I showed you word2vec earlier, but there's also a doc2vec where you can create an embedding for the entire episode. And then just using the dimensionality reduction here, basically squeezing the 50 dimensions that I created for the episode embeddings into a 3-dimensional space, it's kind of amazing because, you know, color-coded are the 2-part episodes. So you can, it didn't work for everything, you know, there's the orange one, which is not close to each other. But a lot of the multi-part episodes actually did end up in the same space. Sorry, I find this really cool. So moving on, because time.
Yeah, so this KNN algorithm working here behind the scenes is interesting, but it has a few problems, right? The complexity of it is a big deal. So back to the engineering land. This is not what you take into production, right? Because the larger your data set becomes, the more time it will take to look up your nearest neighbors. You will have to sift through all your embeddings each time. So we need to solve that if you go into production. So how can we do that? Imagine you would draw these random lines, orange, blue, and green, throughout your embedding search space. Then you could, for any given dot embedding there, calculate whether it's above or below that line, right? It's actually basic math. So let's interpret above as a 1 and below as a 0. So for the red dot, that means it's above the green line, below the orange line, and below the blue line, right? So that's a 1, 0, 0. 1, 0, 0. That's a binary number. You could convert it back into the decimal domain. That's number 4. So, in fact, these lines are dividing your search space into 7 unique buckets to which each embedding belongs. And that kind of simplifies the whole search for your nearest neighbors a lot. It gives you a way to approximate finding them. Because if you simply store the bucket number together with each of the embeddings, you simply need to grab for any given embeddings for which you want to find the nearest neighbors, the bucket number, and try to look for any other embeddings that are part of that bucket number. This is called locality-sensitive hashing, and that's the principle on which this works. Now, this simplifies your search into a nearly constant time operation. But agreed, I mean, there's still problems with that. What if your true nearest neighbor, for example, is still split by a line by accident, because these are random lines? As you can see with the red dot, the true nearest neighbor is separated by the blue line there. You can solve that. It's a bit out of scope for this presentation. You just basically need more lines. And anyway, focusing back on the engineering part, now you understand the gist of how this locality-sensitive hashing can help you taking things into production. I do want to warn, you probably don't want to implement this yourself. There are frameworks out there that already do this in even smarter ways. Well, exactly similar to how it is done here, but they're battle-tested. And examples here are FICE, that's by the Meta guys, the Facebook guys. You have OpenSearch and Elasticsearch. Well, one is a fork thereof. And they offer this functionality out of the box. So go and grab it. If you, for example, are creating a text input where you want to suggest the most probable next word, you're going to need these kinds of technologies. Now, let's look into an even cooler model to generate these word embeddings. Back to you, Gretel.
All right, so we started off with bag of words, moved to word embeddings with word2vec or doc2vec. Now, obviously, we cannot finish our talk without talking about the latest state of the art in the NLP world, which are the transformer models, or Bert. Or, Bert and all his nephews and cousins, I have to say, because there's many variations of these transformer models. So they're deep learning models. They apply a very specific mechanism of self-attention, and basically that gives them the ability to take into account the context when creating a word vector. So in this little example, he's robbing a bank. The riverbank was overgrown. If we would feed these two sentences in a word2vec model, then the word bank would receive exactly the same embedding. Not with Bert. So you actually will see that the embedding for bank in the first sentence is different than in the second sentence, based on the context of the sentence. To get started with transformers, we highly recommend Hugging Face. I mean, we deeply rely on it for everything transformers, to learn things, to use their libraries to make things easier. And so we've used those libraries as well to play a little bit with transformer models on our Deep Space Nine data. Oh, this didn't go well. All right, so the first thing we did was actually take a pre-trained Bert model. Keeping the timing to consideration, I'll have to go a little bit faster here, but we started with the still Bert, which is half the size of Bert. So that being said, be prepared to be patient. So bag of words is a couple of seconds, word2vec is maybe a minute. This thing is hours or days, depending on how many epochs you train it for, and laptop, no good, you'll need a GPU. So I'm showing it on the laptop, but that's not where I trained it. So obviously, if we would, this is a masked language model that I chose in this particular case, so we can ask it to fill in a mask, a blank, in a sentence and see how good it does. And so obviously, if we ask this kind of sentence, Commander, mask is talking over the intercom, with the pre-trained model, what we get is obviously not Deep Space Nine characters. We get McCoy, Jones, James, etc. So what happens if we fine-tune the model? Well, in this case, we decided to fine-tune for 20 epochs. It actually sort of bottomed out around 13, to be honest. I didn't really get any improvement after the 13th epoch. This took about an hour to complete, and if we have a quick look at what kind of results we can expect. Sorry, I hope you're not getting seasick, me scrolling this fast. So to test the model a little bit, let's give it a few inputs and see how it did, fine-tuning. Well, that same sentence, so earlier you saw none of the replies, none of the outputs were Deep Space Nine characters. Now we see some Deep Space Nine characters appearing in the first and the second position for sure, but they're not the right. I mean, it's not the one I wanted there. It's not. It shouldn't be the most likely ones, right? We want Sisko to appear there. If we look at he's drinking a cup of, we don't get the Recticino yet. It's still really based on Wikipedia, that it was originally trained on. Of course, we could fine-tune, play with this for many more days and try different mechanisms, but we decided, well, what happens if I just try to train one from scratch? this was a little painful exercise, I have to say. I mean, a little frustrating along the way. Notebook crashed a couple of times, had to restart, etc., etc.
Hates Python.
And yeah, probably. So I looked at what happens after one epoch. Of course, nothing much. Then I looked at what happens if I train it for another 4, so a total of 5 epochs. It started to move in the right direction, so I was kind of encouraged. So I let it go for 10 epochs in total. It was a multi-day exercise. And let's have a look at what we get after 10 epochs. Well, our first example here, he's drinking a cup of still coffee and stuff is at the top, but bingo, we've got a Recticino. And now, in all honesty, they do drink coffee in Deep Space Nine, so it's not wrong. But a Recticino is there. Some beeps and the image of Gull do cut. Correct. First answer here. This one everyone knows, right? 2, beam up, right? So we get it as our first answer. So 10 epochs, well, it gave us a good language model, I would say. Just looking at these anecdotal examples. All right.
All right. So transformers, yeah, these are awesome, right? I mean, if you've seen any of the presentations here on AI, transformers are all over the place. They can really solve insanely complex problems humans are barely able to solve. So they're awesome tools, but there's a little bit of a but. I mean, Gretel already mentioned it. They require quite a lot of time to train. They require dedicated hardware. You need a fancy GPU, maybe in the cloud, maybe locally. That's up to you. But this is something you need to take into account. So if there is an opportunity to solve your problem with a simpler model, please, by all means, do that. Don't be blinded by all the fuss around it. Look at your use case and take what is most probably going to solve your problem, right? And this is something we experienced firsthand when we were doing all this fun stuff with machine learning. Sometimes the simplest can already solve 90% of your issues. So check your requirements before you wander off.
That's true, and sometimes we start with something fancy and
We
the
trash
reality
it.
kicks in and we just go for something simpler and the accuracy is still, good. So.
Yeah, definitely. Quick question to the audience. Who has ever played with a transformer model? Please raise your hand. All right, 4, 5, 6. That's nice. Who currently has a transformer model in production serving requests of customers? One.
We've got a pre-trained one, though, into full disclosure.
Two, sorry, I didn't see. Yeah. All right, this is already good.
Yeah.
Next slide, please. So this seamlessly takes us to the engineering side of things. This is exactly the kind of response we anticipated. There are many companies setting up proof of concepts with machine learning, but it is incredibly difficult to take these proof of concepts all the way into production. And it's really a challenge. And one of the main challenges here is the handoff between engineers, data scientists, and operations, IT operations. And in order to have your machine learning journey successful, you really need a close interaction between any of these 3 big pillars. Now, to solve and to deal a little bit with that problem, there is a need for a set of reusable processes that can help you support operationalizing your machine learning problems. And those all fall under the umbrella term or the buzzword MLOps. So let's look a little bit into this MLOps word and what it means to us, or maybe to you.
All right, so it starts with discovery, and that's basically what we've done in the first half, trying out the different models in our Jupyter notebooks. And I actually come from a sort of an internal data science team, and I would say, your discovery phase will probably take you 40%, 50% there if you're just, your customers is internal. But working for Collibra, our customers are external, so our ML solutions have to go into a product and have to serve customers in many different ways, situations. So in that case, really just having your discovery phase really only takes you 10% of the way. And so let's look at what comes next.
Yeah, there are quite a few more dots to fill in this slide. And the first one is the basis of all, right? you need storage and you need a scalable infrastructure to help you out a hand here. For the storage, you'll typically want to store 3 types of data. One, that is your data set, so the Deep Space Nine scripts in this case. You cannot rely on this fake website to always be online and start scraping it off every time, right? 2, the model, its architecture, its parameters. Once you train it, you don't want that stuff to go lost, so you need to store it somewhere in a structured way. And 3, you're gonna need to store all the metadata that these models are producing, maybe during training, evaluation, testing, even in production. I'm talking about, like, for example, in production, how accurate is the model predicting the results of the end user? You need to store that in order to feed back into your process and improve your process. So you need storage. Second, you need that scalable infrastructure. So even if you're managing a very small model and it's very easy to train, you cannot outrun the fact that you need to manage that infrastructure. So, and I'm basically trying not to say Kubernetes, right? Everyone knows it has a huge role to play here. So you should probably look into that if you want to roll out machine learning solutions. And if you're okay to lock yourself into any of the major big cloud vendors, probably you should do that because they will offer you an amazing experience out of the box. But if you're not okay with that, and this is in fact the case for Collibra, we need to roll out to any cloud vendor, then you need a bit more of a generic solution. Maybe you need to look into technologies like Terraform, which will abstract you from the individual cloud vendors. So you need to take care of these corner cases. And in fact, there are a few more other corner cases. What about your existing infrastructure? You cannot kind of ignore that, right? It needs to play together with it. And what about mixed cloud and on-prem environments? I mean, everyone is looking at the cloud, I understand, but there are sometimes cases, like in our case, where customers say, sorry, our data never leaves our premises. This is sensitive data. You should not drag it all the way into a cloud, and we understand that. In fact, we have a dedicated solution for that called Edge, which is nothing else than making sure that there is some sort of compute mechanism available, a small mini cloud environment, all running on their premises, isolated.
Yeah, believe it or not, as a data scientist, we actually have to train models without seeing any customer data.
From
That's
time
quite
to
a
time
challenge.
that happens. Yeah. And there are also probably air-gapped environments. It's maybe for security, even heavier security reasons like defense. They all have their environments completely air-gapped. There is no internet connection whatsoever. So you need a more isolated software delivery pathway for this. Okay, so now we have a notebook discovered in our discovery phase. We have some infrastructure, we have some storage. What's next? How can we take our Deep Space Nine models into production? Next slide, please. So it's all about the data, right? You need to store it, but you need to do some other stuff with it. In fact, there are quite a few questions you will probably ask yourself about that data. First and foremost, do you understand it? I guess we do in this case. It's the Deep Space Nine scripts. It's not that hard to understand. It's just the subtitles of each episode. Okay, great. Do we trust it? Well, I don't know. Maybe some translations are a little bit off. Maybe some episodes are switched with one another. And this already brings us to the next question. What about the quality, right? If the translations are off, the quality is probably not that good. We don't know in this case. And the lineage, that's also a question. Where does this data come from? Is it maybe aggregated from different data sources and then joined up into one bunch? We don't know. We just downloaded it from this website, right? If you have troubles answering any of these questions, you probably need a data governance or a data intelligence solution, and that is kind of what Collibra is all about. But okay, enough of the sleazy advertisement. Let's think back of our notebook. What do we need to do with that notebook in order to move that data processing into the cloud? Well, to put in very generic terms, you need to lift it out into a reproducible training pipeline. A data pipeline. Training pipeline is another thing. And the keyword here is reproducible. So something running on Gretel's notebook is not reproducible. I cannot click on a button and automatically generate myself a new data set that is ready for training my next model. This is not reproducible. You need that available at a click of a button, maybe at an event, maybe on a schedule. That's what we mean with reproducible. And there are, again, some few considerations here. Well, first of all, you probably need a framework, an ETL framework. I'm not going to try and sell you any specific frameworks. There are a bunch of them. Internally, we're using like 4 or 5. It really depends on your use case, but you probably need one to extract, transform, and load your data in some way, right? And
well, we'll name one.
yeah,
Name one?
Fortran is there, but
Astronomer.
Astronomer, Google, we're also using, and AWS, we're also using some AWS stuff. So plenty of choices out there. Maybe a bit more important from an engineering point of view is, well, one thing close to my heart at least is please treat that data pipeline exactly the way you treat any other software project. So version it, test it, peer review it. So all the same quality principles are applying here. And yes, that data pipeline will need to be able to scope with scale, but be a bit flexible there. If your data set is small, if it's only 20 megabytes, maybe you don't need a full Spark cluster to process it. It depends. So I think we should be flexible there. Yeah, and again, make sure that you understand what is the access limitations to your data. As I explained, sometimes you just cannot directly access the data from your pipeline. So maybe your pipeline needs to run in a certain specific environment that is close to the data. So that's the data processing side. Next slide, please. What else do we need? So now we have the data processed. We have generated a data set that can fit the training of our model. We have some scalable infrastructure and storage. Next thing we need to do is we need to lift out the code from that notebook in a very similar way into a repeatable training process that again can be triggered by hand or by event on a schedule. And it's supposed to do the training each and every time in a reproducible way. So you need a training pipeline. Again, frameworks out there to help you. In fact, we have an internal tool for that, but maybe some examples here are MLflow or Kubeflow. Well, mostly Kubeflow will help you with this to set up that training pipeline. And there are, again, a bunch of others. So do your homework and check what is most applicable to you. Once you have that training pipeline available to you, the final output of that training pipeline should be some sort of easy to deploy unit, right? And I'm again trying not to say Docker and Kubernetes because, yeah, I mean, this is probably the way to go. But I try to be a little bit more agnostic here because, for example, MLflow has a little bit of their own opinion on how you can wrap up and package a machine learning model. They have their own format. Maybe it can be interesting to you. But it can definitely also produce Docker containers. So you need that uniform unit of deployment that is rolling out machine learning artifacts on the go, reusing your data pipelines on the spot. So once you have that, you'll also have the opportunity to start testing those models into various different environments, right? You can start testing it into an environment that is super close to production, but just not yet. Or maybe you can do A/B testing, where you're taking part of your customer base and routing it to your latest version of your model and seeing how it behaves over time. So that's the operationalized training and model deployment part. Next step. This is all about serving your model. A machine learning model does not talk the language of your customer. It does not have a REST API. It doesn't have any of these considerations. So how do you do that? You need something in front of that. You need a model service that can help you serve up the requests incoming from your customer, maybe. Maybe enrich that request with any additional data that is needed to do a prediction on your model, and then go and grab a model, do the prediction, and serve the answers all the way back up to your end user. So you need that step in between. And you can implement this in various ways. You can do that in an online fashion, as I just explained, where you're directly going to a model that is maybe already spun up. But maybe you can ad hoc spin up multiple models and start serving out batches of requests in one go to optimize this. Maybe you do it in a streaming fashion. In our case, for Collibra, we're doing both online and batch prediction for this. And then for the last, but oh so important part of our ML ops stack, over to you, Gretel.
Sure, and that's often where the ball gets kicked back to the data science team, right? So once the model is in production, that's obviously not the end of it. We have to measure how good the model actually is doing once it's serving real customers. And as mentioned, we often actually we have to train our models on data that we have collected ourselves. We do have to do a lot of Mechanical Turk stuff ourselves. And then once it's in production, it's sort of like, okay, you've trained to hit the target over here, but the target will be in a slightly different place once you're let it out in the wild and you have all these different customers using it, which are obviously there's differences between them, how they use the product even. So we have to monitor how is the model performing, do we have any data drift, do we have a performance drift, and even, you know, sometimes how fast, you know, if we do have a few issues now with TensorFlow, upgrading TensorFlow from 1 to 2, and every time we upgrade, the performance goes down. So then we often start sort of go back to the data science team and say, well, you know, can we redesign the model? Can we refine tune it? Maybe use something else that's out there in the market by now. So it's a circle, really. So it's never really done. It comes back, we try new things, and then if they are successful, we deploy them again. All right.
So indeed, we've now come full circle. We really had to rush through this stack. If you're interested in having a little bit more detail or like reading a very similar explanation, grab the Practitioner's Guide to ML Ops by the guys from Google. It's a really awesome white paper.
So this was our little machine learning example using Deep Space Nine from a data science perspective and from an AI engineering perspective. I'm so happy and lucky to be part of a wonderful team in Collibra. We have data scientists within the team, we have ML engineers in the team, and of course we also have ML ops people in the team, and each are crucial to get this whole thing done. It really takes a village to put something in production. Again, having come from an internal kind of situation, I'm learning a lot in Collibra to see what it actually takes to put something like this from an idea, which is obviously also important, an idea, to actually having customers use your machine learning product, which is really cool. So I hope we were able to convey these two perspectives in this presentation.
We'll be at the booth. If you have any further questions, please just reach out to us there. And we really hope you'll have a nice time for the rest of Devox. Thanks.